Yes, am I audible?
Yes, so we'll start we soon. If you have some doubt, you can ask Ganesh. Hello. Can you hear me?
Yes, sir.
Yes, you are not audible.
Yes, sir. You are audible.
Yes. So if you have some doubt, you can ask me. Let the persons join. Meanwhile, you can just ask me if you have any doubts. If any one of you have any doubts, you can ask me. Okay.
Okay, sir. Okay.
So just let us wait for another 1 minute and let the persons join.
Okay, sir.
So do you guys have any doubt from the previous weeks? Or any doubts you faced while solving the assignments, you can just ask. We can have a talk from there. We'll just proceed with the session, okay? So is the screen visible? Hello?
Yes, sir. Visible, sir.
Yes, you can see the slides, right?
No, sir. Slides are little ago visible, but now it's not showing, sir. Yes, now it's showing, sir.
Now it's showing, huh? Okay.
Yes, sir. Visible, sir.
Yes, so I am visible also, right? Just a moment. I think I am visible.
Yes.
And the slides are also visible, right?
Yes, sir.
The slides are moving, just check.
Moving, sir.
Okay. So let's proceed. So if you guys don't have any doubt, I will proceed. Okay.
Okay, sir.
So we'll start with the nonlinear loads. Okay. So as I have already discussed in the week 1 and also week 3 and 4. We'll just mute this. So we have already talked a lot about nonlinear loads, but since you have already a dedicated section for that, we are just going to discuss a brief overview of the nonlinear loads. Okay, so as you can see, the nonlinear loads, there are the nonlinear. What do you mean by nonlinear? Can anybody tell me? What is the difference between? Can
Means,
anyone
sir,
tell me the difference between nonlinear
sir.
systems and nonlinear loads and linear systems and linear loads, obviously. So why the term nonlinear is coming? What do you mean by nonlinear loads? Can nonlinear devices that you see like diodes, first tell me what are the devices that are used, diodes, IGBTs, MOSFETs, what kind of devices are they? Are they linear devices or they are non-linear devices?
Non-linear, sir.
And why we tell them non-linear?
Because, sir, their VI characteristics is not a straight line. They don't follow Ohm's law.
Correct. So now tell me, if I connect such systems, such devices, and form a kind of load, like we have solved in week 1 and week 3 and 4, like diode bridge rectifier with your R load, for example, single phase. Okay. So then in that case, if in those type of loads we use such nonlinear elements, nonlinear elements and linear elements, like systems, we tell nonlinear systems and linear systems. What are the definition? The systems like that which satisfies the Bibo stability and all those things. Okay. So system wise or element wise, they are nonlinear, obviously agreed. But do you find any difference between these two terms? First, just in order to briefly talk about this, we can go ahead with a discussion that, okay, agreed that their VI characteristics are non-linear. Does they mean that they will always lead to the formation of non-linear loads? Can anyone tell me? Can anyone throw some lights on those things? Do if we used some non-linear devices, will the loads also be non-linear? Can anyone tell me such points or such with some arguments they have? Anyone? The question is that will the nonlinear devices or nonlinear elements always lead to formation of nonlinear loads? And also by the term nonlinear loads, what do you understand also? Nonlinear systems you correctly told, but can anyone throw some light upon that? Just we can discuss, okay? So the question is, will nonlinear elements, okay, like diodes, IGBT, MOSFETs, etc., okay, if we use such elements in our loads like diode bridge rectifier, fed R load, okay, like converter based RL or something, RL or E type loads, always lead to forming nonlinear loads. Yes, I want to hear some answers. Okay. Yes, understood the question. What the question is asked? These nonlinear devices, right? So will they always lead to formation of nonlinear loads or what? What? And what is the definition? By nonlinear loads, what is the definition? Anyone, just be interactive. You can turn on the videos also if you want.
Non-linear load. Am I audible, sir?
Yes, yes. You can also turn on the videos. It will be interactive session, right? So you can feel free to turn on the videos and we can have a discussion. Okay.
Yes, sir. In non-linear load, the current is not proportional to the voltage.
Agreed. Correct. But I am asking what the question is that we have nonlinear elements like diodes, IGBTs, MOSFETs, and all those elements where the V is not proportional to I. My question was that whether nonlinear elements, if we use them in some loads like diode bridge rectifier fed R load or thyristor fed R load, will they always lead to formation of nonlinear loads? The question was that will nonlinear elements always lead to formation of nonlinear loads? That is what I meant to say. So definition wise, we can write nonlinear loads means V not proportional to I or VL not proportional to IL. The voltage across the load and the current going into the load are not proportional. We can tell them as nonlinear loads. They are classified as nonlinear loads. But to become a nonlinear load, do always the loads have to be used with some nonlinear elements, or some linear elements can also lead to the formation of nonlinear loads? Or whether these nonlinear elements like diode based or IGBT based or MOSFET based devices can also form linear loads? So this concept should be
Yes.
very important. Huh?
Yes,
So
these devices, they always form the nonlinear loads.
yes. So then you just recall we discussed in week 1 also that diode bridge rectifier single phase and then you have a R load. Okay. You draw the waveform. What will be the
Yes,
waveform
sir.
if such loads, if you connect as, if you call this as VL and I call this as IL, then VL is proportional to IL in such cases. Then how it can be called as nonlinear load? It is not nonlinear load. Okay. So it is, this term is not always true, that even if you have some diode based or thyristor based with alpha equal to 0.
There
Yes.
it is possible that
Correct. So this concept is very should be very clear, that only you will call those loads to be nonlinear loads where VL is not proportional to IL. Not by seeing the devices. Maybe there are diodes sitting there and all those things, but they may not be nonlinear loads. Okay, so obviously you need to have some nonlinear elements for the loads to be nonlinear. Agreed. But the reverse is not true. Even if some nonlinear elements are there, they may not be nonlinear loads also. So that was what I wanted to emphasize on. And one more thing. So nonlinear loads, don't get confused by the term nonlinear loads, that this VL and IL needs to be always sinusoidal. Okay. Linear loads means VL proportional to IL. Okay. Linear loads means VL should always be proportional to IL. Okay. Now someone tells you this is a square wave. This is VL. IL is also like this. Not sinusoidal, but square wave. Is this a linear load? Is this example of linear load? These characteristics? Of linear load? Answer is yes. They may have harmonically distorted voltages and currents through them, or going through them, or impressed across them, but the nature of that load can be classified as a linear load. So nonlinear load and linear loads don't have any relation with the nature of the waveform, neither with the nature of the elements that are used, but with the nature of the, with the correlation between the waveforms of the voltage and currents. Okay. So that was the one thing which I wanted you to understand, that or nonlinear element based loads also may be linear. Understood everyone, or you want me to repeat? This is important because these types of concepts you need to understand and will be asked also in the exam. So anyone has some doubt in understanding this, I can give more examples. Okay. Anyone has some doubt, because this concept is important. Okay. Shall I proceed?
Yes, sir.
Okay. So this, after
thanks, sir.
understanding this
If
concept, Yes, yes.
If
Please go
system
ahead.
if system is linear and elements are also linear, then it will
Correct.
be always linear, non not non linear or
No, 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 no. Then the response should be linear. Okay. The
yes sir.
because the system as well as the elements you have used linear, and you can
Yes
use
sir.
normal LTI system analysis. That's why we do LTI system analysis in those cases.
Yes.
We
Yes
determine
sir.
transfer function, and because whenever you are using any transfer function in any systems, you already assume they are linear time invariant causal systems. Then you apply
Yes.
your initial conditions and then solve. Solving means you are solving on only the linear responses. In that case, it is also dependent. But if you want to do harmonic analysis, like we are doing in this course of power quality, then you have to break it down into different harmonic components, and individually you need to do the harmonic analysis. So in order to make it simpler, we are using these techniques, these power techniques, where we are using power balance and all those things, because LTI analysis is easy, but LTI analysis is considering only one omega. Now, if there are multiple omegas, you either need to do superposition theorem, which is quite tedious. You need to do it for voltage as well as current. But we want the final response. So, in order to determine the final response, it is easier to go ahead with the power. Because you first day I showed you that if voltage has one harmonic component and current has many harmonic component, power transfer will
Yes
only
sir.
happen because of the voltage and the current, that component, that particular component of the harmonic of the current, which
Yes.
matches with that of the voltage. So that's why the power analysis in all these numericals you are seeing is very easy compared to the superposition and all those LTI analysis. LTI analysis for linear systems only. Okay. For non-linear systems, those LTI analysis will also fail. So that's why we go ahead with the power approach, because power balance approach will never fail. Either the system is non-linear or linear, any type. So those LTI analysis may not work everywhere, but this power approach, which we are doing in most of the problems, I can tell you, where whatever formulas we are using or whatever approach we are doing, we are first drawing the waveforms and then going with the power approach. So that approach will always work in those kinds of problems where you have harmonically distorted waveforms. So just remember the Fourier analysis, and if you even don't remember for some of the formulas, like the DC link voltages and all those things, and you can derive also for such some of the specific problems. You can derive if you understand the waveforms. So that will be easy. So you will also see some problems. We have kept three four problems of the nonlinear loads where you have to have some analysis of the waveforms, and it will be easy. It will be just one line problem.
Okay.
So yes, yes, yes. Any questions? Huh.
No sir.
Okay. So after understanding what is nonlinear load, let us understand, just go ahead with a brief overview of the nonlinear loads. What are their impacts? So impacts I already told you. The nonlinear loads lead to increment of the RMS current in the line. And if you have higher rating of current flowing in the line for a same amount of power that you have to transfer, then it obviously leads to loss in the AC lines, because you have resistance, and that I RMS square into R, because RL or R feeder or R line is constant. This is constant. But for the same amount of power to be transferred for these particular nonlinear loads, dominating nonlinear loads, this IRMS increases. So due to increase in the amplitude of the IRMS, or I can tell due to the presence of harmonics, we have more IRMS and magnitude wise. That's why it results in loss in the line. So loss in the line for a power that you are not utilizing. So that means penalty to the consumers, as well as it is of it leads to poor power factor at the AC side. So that's why it is a great concern both for the operators as well as for the consumers. So that's why it should be prevented, both at the generating end as well as at the end, at the distribution end. So the effects are, as I told you, RMS currents increase and losses, obviously poor power factor, poor utilization because the rating needs to be increased but the power is low. However, the rating, since it is more than the utilization factor, is obviously poor. Heating, and for all also, the one thing I want to explain here, can anyone tell me that if you have a weak grid situation, weak grid means, anyone aware of weak grids? Just can tell me. Can have a discussion. Anyone aware of weak grids? What is the meaning of weak grids and where are they prevalent? Anyone? Just we can have a discussion on weak grids and their impact when connected to nonlinear loads. Otherwise, you will not understand this point. Rotating electrical machines. This point you will not understand. So, anyone aware of the term weak grid? We can have a discussion.
No, sir.
Yes, weak grid means that it is mostly prevalent in the distribution end. Distribution means at your consumer end. It is not prevalent in the generating end, because after long length of lines transmitting power in the remote areas where you have long feeders transmitting power to the villages, then what happens? The line impedance keeps on increasing, and when you have a AC grid with a huge means comparable your X by R ratio, this X by R ratio, obviously X should be greater than R of the line, but the amplitude wise mod X and mod R are high. Then the impedance of the grid also becomes high. And where are they prevalent? In long length transmission lines, long feeders, I can tell, in remote locations. So what happens if you connect a nonlinear load at the point of common coupling, wherever the supply is coming after that long transmission distance? Then what happens? That AC means, what is the scenario in those cases? I will draw. Yes, you have grid, okay, and then you have long X and R, okay, and this is the point of common coupling, and there the loads are connected. So if this is more, then if you connect some nonlinear loads here, IL is nonlinear, then VG minus IL into, let's say this is ZL. Now this ZL is significant and these loads are also significant. Then this drop is also significant. However, since IL is harmonically distorted, means this is nonlinear, okay. So this is also VPCC is also distorted. Agreed or not? Then if you apply this three-phase harmonically distorted voltage to the mostly common loads like pump loads or three-phase induction machine or three-phase rotating machines, any rotating machine, then what will be the effect? Can anyone tell me? If the system is a weak grid nature and harmonically distorted currents of seemingly large quantities are being drawn from the point of common coupling, then what will be the impact of impressing that particular voltage VPCC across three-phase rotating machine loads? Can anyone tell me what will it lead to? Because you know that if you have three-phase time displaced currents to three mechanically displaced windings in the rotating machine, it will result in RMF, okay, rotating magnetic field, for which the rotating machines actually rotate. AC machines, okay, three-phase alternating current machines. But what is that effect of impressing a three-phase harmonically distorted, not unbalanced? Please remember, this is not unbalanced. This is harmonically distorted waveform. Because still assuming that there is no unbalance, only you are impressing harmonically distorted voltages across the three points, three phases of the AC machine. Then what will be its impact? Can anyone tell me? Yes, can anyone tell me? In a weak grid scenario. This is prevalent in a weak grid scenario, okay. Weak grid is observed in islands or deserts or remote villages where you have long length of transmission lines, which accumulates to resulting in relatively larger values of X and R, which leads to increment in the line impedance. So can anyone tell the effect? So what is the effect? Effect on, you can tell, the rotating magnetic field of rotating machines. Yes, so most of you can tell, I think. Most of you must have come across AC machines during your BTech or something. What will happen if I impress harmonically distorted voltages, balanced but harmonically distorted voltages of same amplitude, only time displacement is there 120 degrees, to the three phases of a rotating machine? Anyone?
Crawling, sir.
Yes, partially possible, but crawling is more or less related to the geometry of the rotor and all those things. Okay, It happens also in sinusoidal, if sinusoidal voltages are also applied. Okay. So anything other than that, what will happen?
Yes.
Apart from leaving all the phenomena that are quite prevalent, even if the voltages are sinusoidal, what other additional phenomena or other disadvantages may happen? This harmonic, because one thing you can understand, whenever we apply harmonically polluted voltages, they have their own harmonic components. So can anyone tell me, if I apply three third harmonics? First tell me, can third harmonics exist in a three-phase three-wire system? Three-phase three-wire. Can third harmonics flow in three-phase three-wire systems? Fundamental we know, it's rotating, it results in rotating magnetic field. Third harmonics, will there be any third harmonics due to presence of harmonically distorted load currents? But will they have third harmonics?
No, sir.
Yes, why no?
But because it is 120-degree shifted, so third harmonic get cancelled.
No. 120-degree shifted who? It is the fundamental which is 120-degree shifted.
Okay.
If it is third harmonics, what is the meaning of third harmonics? V1 equal to V sine omega t, or V1a equal to V sine omega t. V1b equal to V sine omega t minus 120 degrees. Assuming ABC phase sequence, just see this phasor diagram. And V1c for the third phase is V sine omega t minus 240 you can write, or plus 120 you can write. Up to this much is clear. What is V3a? V, this you can write as V1, small v1. This is V3 into sine 3 omega t. Because third harmonics rotate with 3 omega. V3b equal to V3 sine 3 times of omega t minus 120, which results in 3 omega t minus 360 degree. Agreed or not? So 3 omega t minus 360 means it is nothing. 3 omega t only. Okay. And V3c equal to V3 sine 3 omega t plus 360 degree. So they are all coherent. Okay. Means that the AC, if the phasors are like this of the third harmonics, are they DC or AC quantity? These third harmonics, are they DC or AC? Anyone, just have a discussion. You will get your doubts clarified. Okay. So this is a good place that you can ask questions and you can get your doubts clarified. So be interactive. Okay. So third harmonics, these waveforms, if I denote them with such co-phasors, are they DC quantities or AC quantities? This phasor. I hope the screen is visible, right?
Yes, sir. Visible, sir.
Yes. So please answer then. What is the significance of these co-phasors? Are they AC or DC?
AC phasor, sir. But
Yes, AC phasors. But what is their significance? That they are not phase displaced. All are
yes,
sinusoidal like this. 1, 2, 3. All
yes, sir.
are overlapping. So such currents or such voltages, if you impress in a three-phase three-wire system, the KCL will be violated. Kirchhoff's current rule. Because
Yes,
star-connected three-phase loads, this is the source, and these are the loads connected with loads, some loads. Now, this point you cannot satisfy KCL if the third harmonic currents flow. So third harmonics can never exist in three-phase three-wire systems. Please remember that. Third harmonics flux may
yes,
exist if some transformers are connected, and since in the transformer, three-phase three-winding transformer, due to absence of third harmonic in the current, the third harmonic flux appears due to the BH nonlinear loop. But the third harmonic
yes,
current not flow in the line. That is clear. So now fifth harmonics. What is the fifth harmonics? How will they look like? if this is the fundamental ABC rotating in anti-clockwise direction in ABC phase sequence, how will the fifth harmonics look like? Fifth harmonics means 5 omega. So if it is 5 omega, then the minus 120 will become plus 120. If you multiply 120 with 5, as we did for the third, if you same you do for the fifth, it will rotate in the opposite direction. And the seventh will rotate in the same direction as that of the fundamental. Hope these concepts are clear with you. Okay. So if 5 omega for the same sequence ABC, why ABC? Because if you sit here, you will see first A will come because it is rotating in this direction. First A will come, then who will come? B, then C. For the fundamental, for the fifth omega, that is fifth harmonics, first A will come as it was, then C will come, then B will come. For the seventh harmonics, first A will come, then it will follow the fundamental. So it is rotating in this direction, and it is rotating 7 omega in this direction. So as you understand, due to applying that harmonically distorted voltages having first, fifth, seventh harmonics, because third harmonics cannot exist, obviously those will lead to different kind of torques and RMFs that will try to rotate the machine in different direction. For that, what will happen? This will lead to frictional losses as well as rotational losses combine of friction and windage loss. Okay, and they will lead to obviously damage of your mechanical equipments that are the bearings are there in machine, and all the shafts and all those things will get damaged. The machine will get damaged due to presence of electrical harmonics that is in the applied voltages. It will lead to mechanical damage of the machine as well as losses from a mechanical perspective. So that's why these nonlinear loads have quite a large potential, and it can do much damage to those systems, to those electromechanical systems. And also you have some oscillations in the machines which may lead to power system instability. That is also very common, because in the normal situation also, due to the imbalance in the generation and the mismatch between the generation and the load demand, you have such low frequency oscillations. Now due to presence of these nonlinear loads, these oscillations becomes more prevalent, and this oscillation translates from one synchronous machine to another synchronous machine, and this can lead to full collapse of the power system. So this nonlinear load mitigation at the AC side is more important, because loads will. One thing, by nonlinear load compensation, what do you understand? These load harmonics becomes completely eliminated, or they are compensated? What is the difference between elimination and compensation? Can anyone throw some light upon this? We have the AC mains, we have the load PCC point, and the loads are drawing. For example, if you connect some thyristor based loads, they will draw harmonically distorted currents. Can you prevent that from happening? Like this SMPs also, they will draw harmonically distorted currents, IL. So I don't want my IG to be polluted. IL is polluted. I don't want my IG to be polluted. What I can do? I can inject those harmonics through some other compensating devices such that it does not reflect at my AC side. Because if it reflects in the AC side, it will disturb the other components connected to the grid due to this load. So I compensate. I don't eliminate. Elimination is not possible because loads will draw whatever current they want, depending on the nature of the loads. You cannot restrict that, but you can compensate for that through some proper control techniques, which we saw in the DStatCom. So DStatCom, the voltage source converter based static compensating devices have that feature of harmonic compensation, harmonic current compensation. So harmonic compensation is done to prevent the harmonics from reflecting into the grid. This point is understood, right? We don't eliminate the harmonics from the load. Harmonics from the load cannot be eliminated. Load will draw whatever current it wants, depending on the nature of the load. But we just translate the harmonics from appearing into the grid through some other shunt compensating path. I'm talking about the current, okay? Voltage quality is done by the DVRs and all those UPQC things by connecting the series. Concept is same, okay? So all your daily loads like these printers, computers, as you have seen in the lecture also, I thought it might be interesting to just talk about this. And high frequency welding machines, all those current transformers and all those connected with electronic controllers, your fan regulators. You know what are these fan regulators made up of? Anyone?
Diode, sir.
No, it is of a device. It is triac.
Yes, sir. Tracks.
Yes, such that the voltage drop is less. To achieve the same functionality, controlled, we use controlled devices but with lesser drops. So your efficiency, your power efficiency improves, right? In controlling, you can use nichrome also. Those previous days we had those registers, right? Variable registers, but that will lead to power loss. So we use track, but these are all only. Hello, am I audible? Hello.
Yes, sir. Audible, sir.
Yes, yes. You want to minimize the voltage drop and increase the efficiency for this given rating, right? So we use tracks, and but they are all non-linear because non-linear elements. Okay, they will lead to non-linear nature of the currents. So the medical equipment also dominated with electronic loads, controllers, and all those things, sensors, which will lead to DC offsets and all those non-linearities in the currents. Basically, the current-based quality problems we have predominantly in the day-to-day practical applications, as you can see. All the electronic loads, everything, your mobile charger and all those applications are non-linear. As you might have seen in the lecture also, the HVDC transmission lines, there also we have current quality problems because the presence of these thyristor-based converters and the large inductance that you want to make the DC side current continuous, right? But it will lead to harmonics and your reactive powers at the AC mains. So you need compensating devices for that. At the compensating devices such that your grid side power quality and all power factor requirements are maintained. Okay, power quality standards as per the IEEE 519-2022 standard, right? You just look it upon in the net. You search it with IEEE 519-2022. You will get a document, a PDF document, and just go through it. It will discuss the current quality standards as per industry standards, that how to actually model your system such that it, and what are the requirements from a grid operator's perspective, that you should not throw more harmonically distorted currents, and if you have more harmonically distorted load currents, you need to compensate them and then connect your system with that of the grid, because you cannot push that high harmonically distorted currents into your AC mains, right? There are some standards, so it is 5% allowed at the grid side. You cannot push beyond that. Okay, so all electrical equipments connected with some converters or some controllers electronically adjustable, those drives all draw non-linear currents, but we don't let them reflect those currents or those harmonic distortions into the grid should always be protected from the harmonics, right? So these are all the non-linear devices, as you can see. I will just skip up on that. Yes, based on the converters also they have explained. But please be careful that not all the converters draw harmonically distorted currents. It depends upon the converter plus the load, plus the nature of the load. They will result in declaring that if whether they will draw harmonically distorted currents or not. Just I gave you the example of diode bridge rectifier with R load. It draws linear currents. So don't conclude my explanation in a way that, okay, I see a converter and it will draw, that means it will draw harmonically distorted current. Not like that. Just see the system, the converter with what it is connected, and then you judge whether it is drawing linear or not currents. So non-linear load and harmonic distortion are two different things. Okay, non-linear load and harmonic distortion are different entities. So can anyone explain that whether the linear loads can I will write the question. Can linear loads lead to harmonic distortion? Give me one reason for that. Any one of you? If the load is linear, can it lead to harmonic distortion? Yes, any one of you can answer. Okay. So I just gave you the example, right? That linear load means V proportional to I. Okay. So V and this is I, VL, IL. But they are harmonically distorted. Okay. So linear loads does not mean that they will draw linear currents. It depends upon the voltage that you impress upon that loads, and it will declare the nature of the current. So both upon the system as well as the nature of the voltage that you are impressing will decide whether they will draw harmonically distorted currents or not. Accordingly, we need to compensate. Okay. Is this concept clear? I can maybe in the exam it can be asked. Okay. Based on some assertion and reasoning questions. So is this concept okay? Anyone, if you can tell me if you have any doubt. Just remember, nonlinear loads and harmonic distortion are two different entities. You cannot just see the nature of the load and comment that okay, it will not draw harmonically distorted currents. I need to give you two information. First, the nature of the load, and then the nature of the voltage that I am drawing, impressing across that load. That will decide whether it will draw that kind of currents or not. Okay. Okay, so it also depends what is the nature of the system, that it is a three-phase or a single-phase system. So you must understand that it will declare whether it will draw what kind of harmonics, just as I told you. That for three-phase system, third harmonics will not exist. Similarly, so the waveform shape also changes based on system to system. So these are all examples of such devices that are already present and lead to dominant distortion of the load currents and lead to the nonlinear loading at the point of common coupling. So obviously, do you understand by the nature of the loads, meaning current fade and voltage fade? Because we are moving to the passive filters after this. So understanding the nature of the loads, not only from a nonlinear and linear perspective, but also from a current fade and voltage fade and all those power quality based definition, that when you deal with the converters, you need to understand that obviously the converters are leading to those nonlinear loads, but nature of the loads also can be classified based on voltage fade or current fade. Do you understand what the term current fade and voltage fade means? Because this has been extensively used in the lectures. So you need to have a clarity upon that. Anyone has any doubt in the term current fade and voltage fade? And if you don't have any doubt, any one of you can explain me what are the definitions. I will hear from you. Okay. So just explain me what are the definition of current fade and what do you understand by basically current fade loads? Obviously non-linear loads and voltage fade non-linear loads. Can anyone explain? This feeding, what is feeding, at which side it is talking about? Okay. Yes, can you explain? Any one of you can explain?
Means we are giving current source or voltage source from the input side.
Yes, which side you mean by input, and feeding, which side you are feeding? Actually, what you are feeding, just throw the clarity upon that.
Feeding means ultimately we are giving to the load. And
Yes, but which side is the load sitting? DC side or AC side?
okay.
Because these terms have been used extensively while moving to the module of power filters. Okay. In the power filters also, when we will give you the examples of shunt and active passive power filters. Okay, shunt and series power filters, passive power filters. Then also I will use these terms that to explain whether you will use passive or whether you will use that is passive series or passive shunt. That will depend upon what is the nature of the loads that are used there. So first, to understand those concepts, You need to have a clear understanding of what is current fed nature of nonlinear load and what is voltage fed nonlinear load. So by current fed, what you understand is at the DC side, please remember, at the DC side, you have either a current source or a load that is drawing a fixed current nature, or a current source that you can model with current source, whatever he was telling. And voltage fed means there should be sitting a voltage source at the DC side. Then only we will term it as a voltage. Actually, we term it as current source converters and voltage source converters, but the perspective here is different. We are feeding the AC or DC side, the DC side, with such voltages and currents of fixed amplitude, and they are behaving as a load, like in HVDC systems. Okay. In HVDC systems, you have thyristor based this link and then another thyristor. Okay. But this current is continuous. So we can model it using a current source sitting at the DC side of both the converters connected in back-to-back fashion. So I can model it as current fed type loads. Obviously, because in the AC side, you can tell that, okay, I have connected some loads. This can be modeled as a load. Agreed or not? This can be modeled as a load, right? Which is current fed, because as a DC, you have a fixed nature of current load. Okay. So please remember the current fed type nonlinear load. Why nonlinear? Because there is the converter sitting there. And a VL is not proportional to IL. VL is impressed sinusoidal, whether IL is only toggling in nature. I told you, na. I drew the waveform also. IL, what is IS? VL and IL. IL at the AC, okay, AC side. VL also, I will see from this perspective. Okay, this is a load to me and connected to the point of common coupling. Then what is VL? VL is sinusoidal, grid voltage, but IL is toggling. You remember the waveform I drew for that fixed thyristor converter with fixed load, current load, DC current. Remember in week 1 we solved the problems also. So if you see the source or the supply side, the current will be toggling in nature between plus maybe plus I DC to minus IDC. If this is IDC, this is plus IDC minus IDC. Obviously with some firing angle shift, because this is a thyristor and alpha shift will come. But understand the perspective that this is a nonlinear load. Okay, but how? It is a current fed nonlinear load, because at the DC side you have a current source. You can model that a current source, right? That's why we call it current fed type nonlinear loads. You need to understand that, because in the passive power filters and their classifications, what type of compensating filters means we are trying to mitigate for the harmonics. What type of filters, series or shunt, will be declared by the nature of the loads. So when we'll come there, you will see how the use of those filters differ from the nature of the loads. That's why understanding the nature of the load is very important at first. Whether my load is nonlinear or linear. Okay, then I sorted out that my load is nonlinear. Then what kind of nonlinearity? That is, the load is current fed or voltage fed. That is also important. After understanding all these steps, we'll move on to the next part, that selection of the filters and the compensating devices that we already discussed in week 2 also. So understanding your load is very important from a grid operator's perspective. Okay. Yes.
In the previous slide, sir, it was voltage fed.
Yes, please tell me. Yeah. You are audible. Hello.
Sir, in the previous slide, it was voltage fed.
No. It was current fed, na. You see this load. What is this I naught, right?
Load is taking currents, and there is also voltage drop across the load.
No. You don't understand it like that. That is what I am telling. It is if you understand like that, na, it is very difficult. I tell you, when I tell you like this, na, that you have a long high inductor sitting here, it behaves as a current source, right?
Yes.
Please try to understand, get a feel of that. See, I have not specified this load. Okay, understood. It can be either voltage fed or current fed. Okay, for this, or even it can be uncontrolled also. But since this is a current inductor, large inductor sitting there, you just see the nature of the waveform. What is the nature of the waveform?
Pulsating.
When it
DC.
comes pulsating, when you have a large inductance value sitting at the DC side, which can be modeled as a fixed current source. Okay.
Yes, sir.
Otherwise, it would not have come pulsating, right? It would have come of the sinusoidal nature, half sinusoidal with the alpha angle. Okay. If it was such voltage fade or something like that, uncontrolled also. But I will not call this a voltage fade only because of the reason that it is drawing on fixed current. The load is fed with like a constant current. So it is a current fade type nonlinear load because the current is fixed. Okay. Irrespective of the switching states, the current is fixed. Load current. Okay.
Yes,
Understood
sir.
or not? Yes.
Yes,
So it is
sir.
very important. Okay. This understanding this concept. After that, you move on to the selection of the filters and the compensators, what functionalities you want, such that you protect the grid. Your system should be such that it does not hamper the operation of the grid and disturb the other systems. The main aim of study of power quality, this subject is for that only. All you do, you achieve functionalities and you control the voltage, regulate the current, and do all your operation with the solar and wind. You integrate multiple such inverter-based resources. Obviously, they will also draw harmonically distorted currents, but they should be compensated with some proper devices as well as selection of appropriate control techniques, such that the harmonics does not reflect at the grid. My main point is this. So I should understand my loads, okay, the nature of my loads. Accordingly, I will select based on my cost and economic obligations. I will select whether I want to, okay, I want to go ahead with passive power filters and passive compensating elements like a low cost arrangement for a fixed kind of, more or less fixed kind of loading arrangement. Or I want to go with much advanced compensating devices like the DStatCom, and even in the remote areas where it has voltage based power quality problems like fluctuations and notches and all those things, I will go ahead with much more sophisticated devices like the UPQC, where it is capable of solving both the voltage quality and the current quality problems, such that my grid is not seeing that fluctuations or harmonic distortions to itself. The load will see all those because load itself is of non-linear nature, but the grid, it will appear to the grid, okay, the load is linear in nature because the grid has to operate at unity power factor for the transmission of power to be economical, and all the points they can reach the power, they can feed the power at unity power factor, because that is the best economic option that is left to the grid operators, right? You must understand that why it is very important for the grid operators to feed the power at unity power factor, because that is the best economic option possible, because they have to push minimum amount of current for that given power. If you operate at any other power factor other than the unity power factor, you have to push more amplitude of current to feed the same amount of power. Why you understand that? I hope you understand that, right? That if your power factor becomes poor, your amplitude of current increases in order to transmit the same amount of power, and that will lead to increasing
Yes.
line loss. So the best economic option that is possible to the grid operators, the transmission companies, the distribution companies, as well as from a generation perspective, it is the best economic option to give you the your power which is coming at the home at unity power factor. Then after getting that power and at the point of common coupling, after that whatever you will do, it is your system. Whether it is an inverter based resource or a distributed generating system, you put some solar and feed to the grid, all those okay. But the grid should not see those power irregularities. That's why we study power quality, and you should go ahead with the standards and incorporate appropriate economic measures, select economically your system as well as the filters and compensating devices. So all those are very important while selection, because first you need to know your load. That is the most important. Yes, please go ahead.
Possible, sir.
Huh?
But is a unity power factor practically possible? Because
No,
most
no,
of
no,
the
not
loads are
possible.
like.
We know not possible, but please understand. From you can only regulate. You cannot control grid. Okay, you are an operator. You are maybe a player, a microgrid player, in the big player in the field of energy. Okay, what you need to do for your particular plant, you must be operating some HVDC plants or some you must be some distributed generation system operator, maybe like that. Think like that. Okay, so what best you can do from your end? From your end, you can compensate for whatever the non-linearities are appearing due to your connected loads. Best possible thing you can do is that only, and control such that the point of the supply that is coming to your system is getting linear currents, and you can maintain unity power factor at that point. You understand what I mean? At the load PCC. So
Yes.
what I'm telling, you have the supply, and this is the load PCC which we are talking about, not the overall central grid. Don't think it in a that way, because grid inertia is very high. You cannot change anything in the grid, neither you can control any power flow in the grid. What I'm talking, you are an operator, okay, distributed generation system or some inverter based resources like solar and wind. You are some player in the market, okay, power, power trading is done and all those things. So at the load point, you want your voltage to be not affected as well as the current. This point I am talking. Maybe there are some other irregularities at the grid side, and grid inductance is also there. Obviously, it will not be unity power factor, but you should be doing just as the power companies or the distribution companies are trying to push power at unity power factor by, they have their own excitation systems and all those filtering techniques such that you can make, and also the compensating devices at those ends, at the transmission ends. You must have read while studying power systems. So transposing they also do to minimize line inductance. They are doing their own measures. Now, from your operator perspective, your microgrid as a microgrid operator or a system operator perspective, what maximum possible thing you can do economically is to push the power or to take the power from the grid at this point at unity power factor. That is the best you can do. You cannot control this whole system, right? So only thing you can do is to
Yes.
maintain the power factor at that load PCC. After that, it will be distorted only because many systems are connected. But for your system, your grid operation is not affected. Like that, I am telling. Okay, you cannot control the overall grid power factor. There is no definition of overall grid power factor. You can only talk for a particular node, because immediate next point when you shift in the line diagram, there are some other loads that are going to come, and the power factor will be different for that point. So node wise we talk, because all the lines are connected in parallel and all are drawing their own loads of own natures. Okay, so everyone needs to take care of their own systems and push power economically such that the overall system is relieved of the harmonic stresses as well as the reactive power stresses, whatever you are getting due to the, mainly due to the loads. Also the generation may have their own, maybe their own faults and all those things, but that are not accounted for in the such systems. Then they can trip their systems and take it out from the grid. But we are talking from a consumer perspective or a microgrid operator perspective. Whatever loads or systems you are operating, you should not disturb the grid operation. That is the basic aim of power quality study. Okay, for that you need to understand your system first. But your system is only the converter dominated source loads. Okay, so understanding these loads are very important, because accordingly you will be selecting the filters which we are talking about last after the mitigation measures. Okay, so compensation as well as filter selections. Okay, so that is important. So all these waveforms we drew actually in the week 1, 3, 2 and 3. Okay, so for all types of loads we drew the waveforms. So just see those and you will get a feel of how the waveforms are getting distorted. Your computer SMPS, that also takes nonlinear loads, nonlinear currents, and battery chargers I already talked about. Your lamps, obviously current and voltage quality problems both will arise for all the systems. So just to give you a feel. Okay, so some 2 to 3 numericals we took just from the non-linear loads to give you a feel, so that you don't forget the analysis that we did in week 1 or week 3. So just read the problem and try to solve it. Screen is visible, right?
Yes, sir.
Yes, just read the problem and try to solve. We'll move fast. We have only 3 problems from the non-linear loads, because we have to go to the filters, right, today only.
Yes, sir.
So you recall the RE loads that we have discussed, right? RE loads based thyristor based uncontrolled bridge rectifier, right? Also, is it uncontrolled, right? So diode bridge rectifier with RE load. So it's single phase, right? So it is just like this, that you have some diode based loads and you have connected your R and you have a battery here. This is 8 ohms, this is 120 volts, and you have the AC supply coming from this side, which is having 220 volt RMS. This is RMS, right? Don't confuse. Many of you were asking. So whenever in AC you have some voltage, this is the RMS voltage. So I gave you. So what is crest factor? Tell me. Of any waveform. Obviously, knowledge of the waveform is important. But what is the crest factor of a waveform? It is some I, let's say peak, the peak amplitude of that waveform divided by what? Average or RMS? Tell me.
RMS, sir.
Yes.
RMS.
So this is the definition of crest factor. Okay. So peak current divided by RMS current. So for a RE load, diode bridge rectifier fed with RE load, you know the nature of the waveforms that I have already drew for you. In the week 1, you can just move and just see. And I also gave you a formula of the RMS current for that. Please remember that formula in the exam. Maybe some questions from the RE loads will come, and that formula is very important. Maybe some shorter versions of that will come so that you don't have to remember the whole part. But okay, you can remember. Okay. I will write for you the formula. So this part is within the curly bracket. This part and this part. And this part is fully within the bracket, right? This is one term. This is another term, which is product with this. Then you have a plus. And then you have this. And then you have another term. All sitting within this second curly bracket, right? This full term. And you have the overall square root. So alpha is 0 in our case, right? And pi minus alpha is the beta. And if you recall, the 2 times alpha was remaining from two sides. So conduction period was pi minus 2 alpha. So that is what we are doing actually. We are trying to take the average value and then mean value, I can say, and then root it over. So RMS, square, mean, then root. So that is what we are doing. If you see the waveform, I have drawn it and explained to you also how the waveform is coming in the first week. So just recall this and then plug it in. If you plug the values in, Vm is actually the peak value. Okay. So 220 into root 2. You put the value and tell me what is coming. E value you know, right? 120 volt. R value is 8 ohms. Pi you take as 3.14. and try to determine what is coming. Alpha, you know, alpha is what? How will you determine alpha? Any one of you tell me? Remember, any one of you? It was the line at which that E and VM was intersecting, right? Battery voltage and that supply. VM or VS, I can tell, supply voltage. So what will it be? But this is alpha. So I can write sine inverse. Yes. Any one of you? E by VM, right? Because this is VM sine alpha equal to E. You equate and take. So alpha is coming how much? Anyone calculate? Do it for me. E by VM you take. VM is nothing, 220 root 2. What is alpha coming? Please do it with me. Hello?
$22.68.
Yes, correct. Or I can write 69, right? Okay. So plug it in. First this alpha, second VM, third your VE, sorry, battery voltage E. This is R, fourth. You plug it in this equation and check such that you don't mistake any terms in the exam. That's why I'm confirming from you. Just apply and find me IRMS. What is it coming? What are you getting as IRMS? I will wait. You just do it. Okay. I gave you this formula also in the week 1 also. You can go ahead and see week 1 video. Week 1 and 2 also you see. We solved there. We derived the waveform and then we supplied this and did a numerical also from here. You just find IRMS, plug it in. Take alpha 0, okay? Because this is uncontrolled. Sorry. One mistake I have done. Alpha is not the firing angle, okay? So alpha is I have used both same notation, okay? So alpha you take as this 22.69, okay? Not alpha is not 0. This alpha and that alpha is different, okay? So this alpha we are denoting by this, the intersection point, okay? So you plug it in here and see what is coming. Just tell me the value of IRMS by putting in these values to the equation. Yes, done. Just put it in and check what is coming. What is IRMS coming? And then also determine I peak. I peak is nothing. VM minus E by R. Simple, right? Check me these two values and determine the crest factor. Three values, you tell me what is coming. All values are with you, just determine. Anyone doing? Or I will write the answer. Hello? Am I audible? Hello? Hello?
Yes, sir. Audible, sir. Audible, sir.
Are so you solve, please solve.
Yes, sir. Service.
I am waiting. You please solve. Huh?
Sir, RMS is 203.65.
RMS value, what you are getting?
203.66. Is it true?
No. Just recheck your calculation.
Okay.
You just do it slowly. I am waiting. Okay. It is important because this many questions can be framed from this particular question.
Okay, sir.
You do it. I am waiting. Please mark the brackets. Don't confuse. This is one bracket, curly bracket, as I am making you see in this slide. And this is another, this is the closing of this curly bracket. And all these three terms, first term, second term, and third term are here, there. With this, you multiply this 1 by pi r square. And then you whole root over it. I am also doing it with you. Just wait. What is R? R is 8 ohms. Vm is known, E is known, pi known, alpha known, Vm, alpha, and all are known. So what is the problem? You just do. What is this first term value coming? Tell me. Let's split it. 0.5 into Vm square. What is Vm? 220 root 2. That whole square. Plus E square. You forgot to take the square root, I think. And do all calculation. Okay. One thing. Do all calculation in radians. Okay. Alpha in radians. Please be careful. Okay. Alpha in radians. What is alpha in radians? So I'm getting inside this full as, once again, 4219 divided by pi into 8 into 8. Yes, I'm getting it. So it is coming as 14.79. And this inside, if you calculate total value, it will come out as 44219. Okay. This total second bracket, whatever is in the second bracket, this is 44219. And when you divide it with pi into r square, 44219 divide your pi into 8 into 8. It will come as 219. So square root of 219 is coming the answer. Just check where you did wrong. You will get 14.8 around amps as the RMS. And what is I peak? Vm minus E by R. Vm is 220 root 2, as I already told you. here. Bm is 220 root 2. And minus E. E is 120 divided by R. R is 8. What is it? It is easy, right? It is 23.89 amps. Amps, that is peak. So peak by RMS. So 23.89 divided by 14.8. What is coming? Crest factor? Around 1.6, right? So this is the answer. The answer is 1.6, right?
1.608, sir.
Correct.
Yes.
Next problem you see. So this is somewhat different problem what we have solved. Just see and then answer. Okay. Question is visible on the screen, right?
Yes, sir.
Yes. Please read and follow. When you are done, you can tell me. So understood, right? You have a three-phase supply of 400 volts, 50 hertz. That is the AC lines that is coming. And you understand by the term 12 pulse diode bridge converter. So it is an uncontrolled converter with two 6 pulse connected in series, right? You have this with its own DC link connected in series with another such PBR in series. So this is forming the DC link. Whatever loads you are connecting, that is modeled as a constant current of 150 amps. You have some isolation arrangements with some transformers to get the phase shift, 30-degree phase shift you want, right? So you have one going here and another going here. So this is the transformer arrangement. So this is how the supply looks like. You have the isolation here, right? And the phase shift. Two sets of star and delta, that phase shift 30 degrees attained, and you feed the DBR based loads, right? So here is one DBR based load and here is another DBR based load, right? So now what is asked in the question is such 6 pulse diode bridge rectifier loads, two 6 pulse, so it forms a 12 pulse, and then it is connected in series to provide 12 pulse that I told you, and supply current distortion factor. So can you tell me? Supply current distortion factor, right? So what is the definition of distortion factor? Just to recall, I am forming these problems, okay? I have already discussed problems, not like this, but fundamental problems. And these terms have already been defined. So anyone recalls what is distortion factor? Yes, anyone? My voice is audible, right? Hello? Hello. Hello. Yes, you are able to hear me, right? Hello.
Yes, sir. Yes, sir.
Yes, sir. Yes, yes. Please respond. Yes. So please go back and just see this problem. What is the distortion factor definition?
Sir, ratio of fundamental component to RMS value of the waveform signal.
Correct, correct, correct. So let me charge my Apple Pencil. It is charges full. So you just give me some insights how to find. I gave you many such techniques to find out the fundamental component. So what is the most easy technique to find out the fundamental component for such systems? Yes, anyone? Just feel free to give your suggestions, right? If you don't express your suggestions, you will be in doubt. So we can use power balance, right? Yes. So power balance is the best method because you know power transfer happens for only fundamentals of voltages and currents. Because voltage is having fundamental only, current is having non-linearities. So, but active power transfer will only happen for the fundamental of current to that of the voltage. So that is the main help that we get by doing power balance. So you write power balance, right? 3 into VRMS phase. Obviously, this is phase voltage into IRMS phase voltage for this side. And with whom will I balance the power? At the DC side of the load, right? So let us, this is VDC, this is VDC. So this is 2 VDC. So 2 VDC into what? Your I naught, which is 150 amps. This is active power balance. And this is VRMS phase 1 fundamental, IRMS phase 1 fundamental. So fundamental you achieved. So what is VDC for a diode bridge rectifier? 3 phase. You know the formula, right? I know, told you to remember 3 root 3 Vm by pi. Vm is phase peak. So I can write 3 VRMS 1 or phase 1 into IRMS phase 1 equal to 2 into 3 root 3 into VRMS. Vm means phase to phase peak. So if I write Vm in terms of VRMS, it will be VRMS root 2. VRMS obviously fundamental by pi. This is 1, small 1, okay? Into 150. This VRMS gets cancelled with this RMS. This is because this is phase. So this 3 also gets cancelled. So what is IRMS fundamental? It is 2 root 6 by pi into I naught. This is I naught, right? IDC I can write. So you got your IRMS fundamental. What is the value? So distortion factor is RMS of fundamental by total signal RMS. All RMS, okay. So what is that RMS, fundamental RMS? You just calculate what is coming. Just tell me value, what is coming?
233, sir.
Okay, okay.
0.9.
Okay.
And
yes, 0.9, correct. And yes. What is the nature of the current at the AC side due to this 12 pulse converter? It is pulsating. As I already told you in the previous slide, due to the fixed nature of the current at the DC, the input current will be toggling between plus 150 and minus 150. So what is the peak? What is the RMS? Sorry, what is the RMS of this total signal? It is 150 only, right?
Yes, sir.
So divide it, what it is coming?
1.559, sir.
Yes, hello.
1.56, sir.
Okay.
Yes.
So how you calculated RMS? Yes, hello.
RMS calculated, sir, from the formula you given. Power balance.
No. That was RMS fundamental.
Yes, sir.
I am talking
Fundamental.
about. Yes, I am talking about RMS of the overall signal. How will the overall signal look like?
Okay, fundamental by RMS.
Yes. Just see what is the overall signal, how will look like. Yes. Hello. Just check the RMS value of the input side. Okay. Because we are determining input side. Okay. So what is the nature of the waveform of the input side? In the line. Okay. Anybody solving? Nobody solving, I guess. So I need RMS value of input side or input current. Overall RMS value, not fundamental. So how do I determine? Yes, any idea? Hello. It's very easy. Just think.
The pulsating DC.
No. Pulsating is okay.
Sir,
But
sir,
it
we
was
have
here. Na?
input of
Please understand. Please understand. It was here. This waveform
Sorry.
was here.
Yes.
I want here.
Degree phase shifted.
Yes, someone was saying something.
transformer, pulse converter.
I derived it also. You just recall. That what is the supply RMS current in case of such if you have known a 150 amps as the DC side current. From I naught, how will you determine? I specifically explained this point in week 1 also. You recall? No one of you recall, right? Will it be pulsating like this? It is a 3-phase nonlinear load. Please recall. It will be quasi square, right?
Yes, sir.
Yes. So then you determine what is the RMS current. For single phase,
Sir,
please note, don't get confused, okay? For single phase, it would have been like pulsating nature. But it is 3-phase, okay? So for sure, it will not be pulsating nature. Now next you tell, how will you solve? It will be quasi square, right?
Quasi square wave with 120-degree conduction in each line.
Yes. Any answers? So primary is star. And one is secondary is star and another is delta, right? So take care of that also and tell me what is the line current. So now you know the nature of the waveform at these points. I hope it is now clear. But you have to also reflect and then add, right? And all turns ratio you assume same. So once you know the currents of any one of the phases for these two, one is star, so that will go in line with this. And but in delta you need to understand that transformations happen phase to phase. So take the phase current of that delta, which is by √3, and then you multiply it with, this current. If it is amplitude I, then it is in delta, it is I by √3, whereas this is I only. And then adding them to, you find this here. That is the RMS value of that. Getting my point? Because everything is 1-to-1 transformation, right? All the turns ratio are same. but I want the line current of the star because line and phase currents of the star are same. So if you do so, assuming the quasi-square nature, you will get 1.57 I naught or 1.577 I naught. Just do this exercise and tell me in the group. So IRMS will come out. Please note down 1.577 I naught. You just tell me with drawing the waveforms, and obviously you do it as a homework, and tell me in the group how you are getting that. Do this exercise, okay? And IRMS fundamental I determined for you, and total signal of the input side. So this is not toggling, right? Quasi square it will be, and obviously you need to do some exercise and then determine it. So power balance will only work for fundamental determination. Overall signal you need to do by seeing the waveforms only. So 1.57 times I naught will come as IRMS overall. So divide these two, and then the RMS, the distortion factor will come out to be 0.989. Just see how it is coming, and answer I gave you, okay? Because we need to move on to the filters. But keep your fundamentals correct, and you do this homework and tell me in the group, okay? How it is you are arriving at that value. So not everything has formula, right? You have to do something in hand also and then see. You can assume that as a formula, but it will not work for all cases. So moving on to the next problem, we have a simple problem where we can have the uncontrolled three-phase rectifier, same like this, and RL load of 50 amperes, constant load current. For this also you need to calculate the THD, total harmonic distortion. So what is total harmonic distortion? Because I took these problems just to warm up your concepts of nonlinear loads. So what is formula of THD? Anyone? It is IRMS harmonic square. Sorry, IRMS harmonic divided by IRMS fundamental. That is RMS value of all the harmonic components divided by fundamental RMS. So you can write as net signal RMS minus fundamental RMS whole root over divided by net signal RMS. Just denoting it with fundamental RMS, and IS1, that means fundamental signal RMS, and harmonic means it is net signal minus fundamental square whole root over. Anyway, you can write. So what is IS1 for this type of, you can use power balance for three phase. So I just determined in front of you 3 into V phase fundamental into I phase fundamental power balance to determine fundamental RMS, okay? Clear? This is what? VDC into I naught at the DC side. 3 root 3 Vm by pi, I told you, into I naught. So what is Vm? Vm is phase peak. It is root 2 times your supply, 440, right? By root 3. You just write it as Vm. Okay, it will cancel anyways. Don't need to find Vm. So Vm is what? This is 3 root 3 was there. Vm was root 2 time V line phase, or phase RMS I can write. This was phase peak. Then peak is root 2 times VRMS, that I am writing, into I naught was there divided by pi. And this was 3 V phase 1 RMS into I phase 1 RMS. So V phase 1 RMS is cancelling with V phase RMS, and 3 is cancelling with this. So it is root 6 by pi I naught. IS1 you can write fundamental RMS. So fundamental RMS I got, and what is the RMS value of the overall signal? As you saw, as you told correctly, it is quasi square. So for quasi square, you know, it is 60-degree conduction out of total 180-degree. 120-degree conduction, and then you root it over and you find out the amplitude. So that pulse is appearing for 120-degree, simple, and 60-60 you gave there, and 30-30, okay, 30-degree is lost. So 60-degree lost, and then 120-degree out of. You can also see for the other part, right? It is another 30 and 30, 60 lost, and then again 120. So just see the waveform, and it will be root over 2 by 3, whole root over 2 by 3 into I naught. So what is coming? I naught means this is 50. So whole root over 2 by 3 into 50 is what?
40.8.
Yes, yes. So you got it as the net RMS and all though this is IS net RMS. So 40.8 square minus fundamental RMS is what? Root 6 by pi I naught. Calculate fundamental RMS. Is 38.98, right?
Yes, sir. 39, sir.
Okay. Divided by fundamental RMS. What is fundamental RMS? Fundamental RMS is 38.98 square whole root over. This is THD. What is THD coming? Calculate. Calculate the THD. Simple, right?
30.9%. 30.9.
So 31%. Okay. THD is 31%. Okay. So this is the answer. So this is how you tackle those load. You need to have the knowledge of the waveform. Just as you in the previous problem also you saw 3-phase and what delta star, all those things affect. Okay. So previous problem, you just tell me how it is coming. You just spend time and use this as reference. Use this problem as reference because similar only, uncontrolled. Okay. And you try to derive for that because that was different from this. So we solved it using power balance and then saw how the using knowledge of the waveform, we just determined the RMS value using the average concept and then root over. So likewise, you determine for the previous problem. Okay. So we'll start the filters briefly. Okay. The passive power filters, which is currently running. And first I want to ask you one simple, so I will turn on my video. My video is paused. Okay. Yes, my screen is visible as well as my video is on, right? Yes, my screen is visible. Yes. I am also visible, right? So as you can see,
Yes,
you first studied compensators as well as filters, right? As you in the next week also you will be studying filters only. So why two things? Can anyone tell me? Why you need compensators as well as for filters? Because you saw passive compensators you had to study. Then next came passive filters and active compensators are also there. Then active filters you have to also study. So a different set is kept for compensators, which we already studied because the compensators like the passive ones, which we studied the problems also, like in week 3 and then in week 4, 5, we did the active compensators. Like, so I will write, you had passive as well as active. The compensating devices, right? So there were the inductors and the capacitors, the lossless elements, right? You remember from week 2, right? And active compensators like the D-StatCom, synchronous static series compensators, the DVRs, that is, the UPQCs, all those you have already studied. Now you entered into the domain of filters. So my question is, why two different things? Can anyone tell me? What are their particular responsibilities? So let's move on to the next slide. Let's see. So mainly, can you see my screen?
Yes, sir.
Yes. So size, performance, losses, anything you can comment for both filters and their compensators. First, tell me why are two different things built to make you to study those two different things? Why so? What are the job of compensators and what are the job of filters? Tell me. what
Filter
extra
will, sir.
yes, what extra thing we are tackling here?
Filter can, sir, filter the harmonics in the currents or voltages, but compensator, sir, will uh, compensate the means leading or lagging part or something like that. It can compensate.
As well as negative sequence components, right? But for a particular fundamental component. So write it. Okay. So maybe omega, the power frequency. So compensators are built in such a way they are lossless elements. First thing is that they are lossless elements, and they're built in such a way that they are functional in the omega, that is power frequency range, and their functionalities are to provide some reactive power compensation for a fixed load. If you are using passive filters, a passive compensator, sorry, if you are using passive compensators, they are designed to function in the power frequency to provide some reactive power compensation or power factor improvement functionalities as well as load balancing, but only for this power frequency. For passives, they are fixed. For fixed loading, they can provide the functionalities. And for active, like as dstatcom and all those things, they can actually compensate for your reactive power and harmonic currents and all those things. Then dstatcom can also provide support for filtering out the harmonics or compensating. So anything you, so what is the difference? Dstatcom also agreed that lossless components like compensators, passive compensators cannot block the harmonics or anything. They can only provide leading or lagging or power factor improvement and load balancing. But dstatcom can provide power harmonic compensation. So what is the difference between filters and dstatcom? Dstatcom can actually compensate for the harmonic components if you apply some direct control techniques, but dstatcom don't filter out the harmonic components. Please understand the difference. Dstatcom can be used to feed in some particular currents to the system, like harmonic components, such that your harmonics don't reflect at the grid side, but they are not eliminating or filtering out the harmonics from the load currents. So the compensators can only compensate for some power, reactive power, or some harmonic components, but to extract or eliminate them from the system, that the filters can do. So there are the basic difference between filtering, that is eliminating out some components directly, and using some alternative compensating devices. So why you need both? Anyone? So these compensators and all those are, as I told you, are functional for a particular frequency. Okay, these passive compensators, whatever you are talking, this particular frequency, but in the for the elimination of some specific harmonic components like higher order harmonic components, you need to block those block those components by appropriately adding some elements, more elements, such that at that particular frequency, like example 5 omega, they eliminate or block that particular harmonic component in the current or in the voltage. So if you have some current quality problem, you will add shunt filters, shunt passive filters. Or if you have some voltage quality problem, this is I quality problem, and this is series passive compensators, you can add voltage quality. So what they will do, they will provide very low impedance for the shunt I am telling to the harmonic component, such that they get extracted or blocked at the mains. And for series, you will, that is the voltage based power quality problems, these are cheap solution, the filters, right? L and C and based with some R, that is to damp out, because if you provide very low impedance for the shunt, then the current may exceed because of the resonance phenomenon. So some damping is required. So the filters, what they do, they completely extract that harmonic component. But the compensators actually compensate for the harmonic component. They don't eliminate. So filters can be actually thought like that it helps to completely eliminate by providing either very low drop across the series path for that particular harmonic component, or low impedance to the shunt path for the current to flow in that shunt path during the current quality problems. So For voltage quality problem due to a particular harmonic component, you need the voltage drop for that particular harmonic component to be low. That way you design some C filters or something like that, and such that for the high, that is, if the voltage, for the voltage I'm telling, and for the current you design some low impedance path. So if it's a voltage based power quality problem, then what you want in that series path, the voltage drop due to that particular harmonic component is the least, such that it does not appear at the PCC point, and others it will just pass. It is like a barrier. Your water is flowing, and it is allowing, that filter is allowing all the harmonic components. That is the fundamental only, and only that fifth harmonic, for example, is provided with some V, delta V equal to 0. So all the voltage that harmonic was in that voltage would have dropped across that particular impedance. So that is how you deal with some filters, that they completely eliminate some harmonic components, and the shunt filters provide path, low impedance path to the higher order harmonically distorted currents. So, but that is a direct approach, that they completely eliminate them from the system. But the compensating devices, whatever lossless, because these filters are not lossless. These filters are having damping. These are, whatever filters we use damping, because the at that particular frequency for which you are designing this filter, the voltage drop or the current, the voltage drop will be very low, or the impedance will be very low for shunt filters. For the series filters, the voltage drop will be very low. So what will happen? For that very small voltage drop, a large current demand from the system may appear. You understand what I am telling? For that particular harmonics, very low voltage will come for a series filter, and then for a shunt, very high current requirement will come because of the low impedance path. So we don't want that, because that will exceed the system rating, current rating. Because if V by, what is I? One second, I'm charging my pencil. So we neither want very low voltage drop for across a particular element, because of which high current may flow, or very low impedance due to which again high current may flow for a given voltage due to the shunt path. So to avoid such high currents, or to avoid such resonance phenomenon, we can add damping, for which you will see that the filters are always accompanied with some resistive elements to provide damping. But compensators, the functionalities are completely different. With control, we just mitigate for that harmonic component. We do not filter anything out. We just extract harmonic content and then tell the DStatCom or some active devices to feed in that harmonic components. It is not eliminating anything. So those two things are different. Even I told you that when we use DStatCom or some compensating devices, it cannot compensate for the switching frequency harmonics that may appear in the voltage and current. So who will absorb that or filter out that from the grid? So that job is to use the filters, which are responsible for complete elimination of the harmonics from the system. So harmonic elimination is done by the filters, right? Yes. So the filters, what they do, they eliminate the harmonics completely. Okay. So in terms of size, I can tell you the, like for example, the active compensators, they are of huge size, right? That the converters, but the filters are in small size, right? Because they are designed for higher frequencies, and for higher frequencies you need very small amount of, to block higher frequency or higher harmonics, you need small amount of L and C's, and to provide the low impedance to those harmonics. And performance by functionality wise, you can see that these, obviously these compensators, that the compensating devices are much more superior, because this can actually accompany the system with multiple harmonic contents. And obviously these filters also can eliminate multiple harmonic contents, but eliminating multiple harmonic components using the filters, the number of components will increase. So we prefer the DStatComs or the UPQCs in such cases where there are multiple harmonic problems. But in order to eliminate some very higher order frequencies, we can use RC filters based first order passive filters, right? To eliminate such switching ripples. So filters, these compensators are always accompanied with filters, and they both work together to achieve the best possible out of a system. And these filters have some losses, because they have resistances, as I told you, due to the damping that is necessary for filters of a particular tuned frequency to limit the current during resonance. And but their losses are very less because the sizes are very small of these filters. The magnitude of R and L and C are all very small, and hence the drop is also very small, and that leads to the very low, I can say 1 to 2 watts, I can tell, for a high rating system. Like in kilowatts, if the system is in kilowatts, you will only account for 1 to 2 watts of loss that the filters may happen across the filters. But they are lossy. Filters are lossy because you cannot just leave the filters with L and C, otherwise they will resonate. But we need to incorporate, because otherwise the filters are very necessary for some switched converters which may reflect the switching ripples in the grid. So to limit that, we use filters. Okay, filters are necessary to be used with such compensating devices. So, but they lead to losses, whereas the compensators are lossless. Ideally, they are lossless, but obviously you know that all the inductors and capacitors have their own quality factors. But for filters, we inherently deliberately plug in some more resistance to damp out the oscillations or to limit the currents. Okay. So I think the time is up. I thought that I will cover the passive filters, but let's take the filters, start the problems of the filters from the next week, the active and passive power filters, and more on them. We'll talk about them in the next week. Okay. So I think we can end the today's session, and you just do the homework and tell me why that current RMS value, how is it coming? Just let me know. Okay. Okay. We can end the session here, right?
Thank you, sir.
Thank you.